Hello and welcome back to A Slice of Physics. We're now ready to talk about mass, weight, and apparent weight. We're going to first understand what mass is, what weight is, what apparent weight is. We're also going to learn how these concepts are related, and we will discuss weightlessness. Let's begin by talking about mass. It turns out that there's not a very easy way of defining mass, but it is sufficient to say that it's a measure of the amount of matter something contains. Or we can say the amount of stuff something contains. It's measured in units like kilograms, grams, etc. And as you know, 1 kilogram is simply 1,000 grams. The prefix K stands for kilo. And even though you might think gram is the fundamental unit, the International Standards Society adopted kilogram as the SI unit of mass. Another key thing about mass is that it's the same everywhere. If you take a can of soda from the Earth to the Moon, its mass does not change. It's still got the same amount of stuff, so it's got the same mass on the Moon as well. Weight is related to mass, but it's not the same thing. We have discussed weight being mass times acceleration due to gravity, and where that comes from is that weight is actually the force of gravity on a given mass. Now you remember F equals ma. That was Newton's second law, and that's a general equation. Any force equals the mass times the corresponding acceleration of that mass. When we take a very specific version of that and we want the force of gravity on a mass, that force would equal the mass times a very specific acceleration. That would be the acceleration due to gravity. And so this force of gravity is called the weight. That would be mass times acceleration due to gravity. And on the surface of the Earth, the acceleration due to gravity is the lowercase g, 9.8 meters per second squared. So that's where we get the equation W equals mg. It's simply a specific case of the standard Newton's second law of F equals ma. The other thing for you to remember is the acceleration due to gravity g is 9.80 meters per second squared. That's true only on surface of Earth. It's not true on the surface of the Moon, the Sun, any other planet, and it's not even true when you leave the surface of the Earth by any significant distance. So let's take an example. Let's say we have Susie, and Susie's mass is 60 kilograms. So that's a measure of the amount of stuff Susie is made up of. And we want to figure out what her weight is. Some of you might be tempted to do a unit conversion from kilogram to pounds using a factor that you might have learned before that says 1 kilogram equals 2.2 pounds. I would recommend that you don't use this. This is not a conversion factor. It can't be a conversion factor because kilogram is the unit of mass and pound is a unit of force. So we're talking about apples and oranges, and we can't equate them with an equation. The correct way to go from mass to weight is to use this F equals ma or W equals mg equation. So the weight of Susie on Earth is mass of Susie times the gravitational acceleration on Earth, which is 60 kilograms times 9.8 meters per second squared, and that turns out to be 588 kilogram meter per second squared, or that's just called Newton. So we got a weight for Susie over here. And as a final step, we could convert this Newton to pounds. Now Newton and pounds are both units of force. We got a conversion factor, so we can change that over here as 1 pound equals 4.45 Newton, and that gives me 132 pounds. Now some of you are doing a calculation and wondering why I'm making such a big deal out of this conversion factor, because if you do multiply 60 kilograms by 2.2, you will get 132 pounds. But that's not a conversion factor because, as I explained, these are different things. They're not measuring the same thing. That relationship, it's not a conversion factor, but it's a relationship, only holds good on the surface of the Earth. And since all but a couple of dozen humans have always been trapped on or near the surface of the Earth, we talk about this as a conversion factor, which it is not. So to illustrate that point, let's see what Susie's weight would be if she went to the moon. So F equals ma works everywhere. So her weight on the moon would be her mass times the acceleration due to gravity on the moon. Now one thing about mass is that it's the same everywhere. So her mass is still 60 kilograms. And the acceleration due to gravity on the surface of the moon we know is 1.62 meters per second squared. And when you multiply that, you get a weight of 97 Newton. And now I can convert this into pounds using this conversion factor, and I would get a weight of 21 pounds. And now you can see that the conversion factor of 2.2 pounds for every kilogram obviously does not work. So the same Susie who on Earth weighs 132 pounds can go to the moon and weigh just 21 pounds. Now you can relate that to astronauts jumping around on the moon and bouncing as if they don't weigh much, which is true, they don't. They still have the same mass, but they don't have the same weight. Okay, let's now discuss apparent weight. As the name suggests, apparent weight is how heavy or light you feel. And this feeling is not just a mental state, it's actually related to the amount of force you're applying on the surface that you're in contact with, or the surface is applying back on you based on Newton's third law. And because of that, apparent weight always equals the normal force in magnitude. Normal force is the force of the surface on you, and in return you apply an equal but opposite force on the surface, and that's what you feel as your weight. So to see how apparent weight is related to weight, let's take an elevator example. Here's an elevator car, and let's say it's just stationary. So V is 0. There's a scale here, and you're standing on it. If we draw a free body diagram of this situation, you are here as a particle, and you have two forces acting on you. You got the long-range force of weight, which is nothing but the force of gravity from the Earth acting on you, and you have the normal force from the weighing scale or the surface that's supporting you. And since you're in equilibrium, these two have to equal. The normal force equals the weight, and since apparent weight is equal to the normal force, you will feel your true weight. Everything is pretty normal. If I take the same situation, and let's say this elevator car now starts to accelerate downward. You press the button and it's starting to move down, and so its velocity vectors will look like this. Small number to begin with, and a larger number a little bit later. So now my acceleration points down. So if I now do the free body diagram of this situation, my net force has to point down because of F equals ma. The direction of net force and the direction of acceleration are always the same. And given that the net force has to point down, my weight is still the same, but normal force has to reduce in magnitude for the net force to point downward. And that's why when an elevator car starts to accelerate in the downward direction, you feel lighter. When you press the button, it seems like the floor is leaving you before you're ready to catch up with it, and for a moment, until things get back to equilibrium, you feel lighter. And that's because what you feel is connected to this. This relates to apparent weight, and so you feel lighter. And lastly, if we take the same elevator car, and let's say now it's reaching the floor that it's getting to, and so it's starting to slow down. And because it's starting to slow down, the velocity vectors look like this, a big number to begin with and a smaller number later. And that translates to an acceleration that points upward. And for the acceleration to point upward, the net force must point upward. So my free body diagram, the weight still is the same as always. That's the force of Earth on you, and since your mass hasn't changed, and since you're still near the surface of the Earth, the weight's still the same weight, but the normal force now grows in order to have this acceleration. And so the apparent weight relates to the normal force, and so you feel heavier. And finally, let's discuss weightlessness. That's the state the astronauts are when they are in orbit around the Earth. In this elevator example, let's take the unfortunate situation when the elevator cable breaks. If it snaps and you and the scale and the elevator cars all start falling to the ground, you're no longer pushing down on the scale. The scale is no longer pushing back up on you because you're both falling at the same acceleration down to the ground. And in that situation, the normal force goes to zero, or more technically, it's not even applicable because there is no contact between you and anything. So in those situations, when the normal force goes to zero or is not applicable, that's when you feel weightless. So to recap, mass is the amount of matter in an object. It's the same everywhere, and it's measured in kilograms, grams, etc. Weight is the force of gravity on mass. So just like F equals ma, a particular application of it is weight equals mass times the acceleration due to gravity. And so it depends on where you are, because the acceleration due to gravity is different on the surface of the Earth, far from the surface of the Earth, on the surface of the Moon, etc. And finally, we discussed apparent weight, which is related to weight, but it's not the same thing. It actually is the magnitude of the normal force between you and the surface that you're standing on. And so if you're not connected to a surface, such as in free fall, you will have no normal force, and so you will feel weightless. Thank you.